Hello from Toronto, Canada. This video is an overview of a paper by Ian Mertz and myself about a new space-efficient algorithm for the tree evaluation problem. The video is divided into two parts. In the first part, I'll talk about the tree evaluation problem. It was introduced in an attempt to separate complexity classes. The problem can easily be solved in polynomial time, but it seems impossible to solve in low memory classes like log space. In the second part, I'll show you a new algorithm for solving this problem with limited memory. The algorithm gives the first space improvement since the problem was originally introduced 10 years ago, and it makes use of some techniques for reusing memory using reversible computations. The first part is older work, mostly done by other people. It's based on a couple of papers from 2010 that introduced the problem. I'll start by describing the problem and its motivation. Then, I'll talk about a couple of abstractions we use to analyze it, called branching programs and pebbling games. And finally, before I move on to the new algorithm, I'll talk about some lower bounds that our algorithm had to work around. So let's start with the motivation. The tree evaluation problem, or TEP for short, is easy to solve in polynomial time, but it's conjectured that you can't solve it in log space. The goal is to prove this conjecture, implying that L is not equal to P. In fact, the gap it aims to close is a little narrower than that. It's in log CFL, but conjectured to not be in NL. But we'll just focus on P and L in this video. So that's the motivation. Now let's talk about what the problem actually is. The input to the tree evaluation problem is a complete binary tree with some information attached to each node. Each leaf has a number attached to it. In this case, 3, 1, 2, and 2. And each internal node has a table of numbers. Given that input, we're going to recursively define a single number at each node called the value of the node. The values of the leaves are already part of the input. To compute the value of an internal node, we need to first know the values of its children. For example, let's look at the left child of the root. The values of its two children tell us where to look in its table. In this case, we look at row 3, column 1, and we find the number 2. Similarly, we look up row 2, column 2 of the node on the right, and we find the number 3. Finally, the numbers 2 and 3 tell us where to look in the root node, and we find the number 2. The output of the tree evaluation problem is the value at the root. There are two parameters to this problem. The first is the height of the tree, 3 in this case. The second parameter is k, which is the range of the numbers at the nodes. In this case, it's also 3, meaning every number is between 1 and 3, and the tables are also all 3 by 3. The size of the input to TEP is on the order of 2 to the h internal nodes times k squared numbers stored in each node times log k bits to store each number. Using this formula for the input size, we can rephrase the conjecture I showed you earlier. Saying TEP is not an L is the same as saying it can't be solved in big O of h plus log k space. Now that I've defined the tree evaluation problem, I want to talk about algorithms for solving it. I'll start by describing branching programs, which are the computational model we're using. Then I'll talk about an abstraction called a pebbling game, which can be useful for both upper and lower bounds. So here's our TEP input again. I'll define a query to be any piece of that input we might want to read. Specifically, a query is either a leaf, meaning we want to read the input at that leaf, or it's a particular cell in one of the tables in an internal node. A branching program is a directed graph, where the nodes are called states. There are two kinds of state. A query state is labeled with a query and has k outgoing edges. The edge you follow depends on the answer to that query. The other kind is a final state. When you get to one of these, the computation stops, and you output whatever the state is labeled with. One of the states is marked as the starting state, where the computation begins. Let's return to our lower bound conjecture. We've written it as TEP can't be solved in big O of h plus log k space. Any Turing machine can be transformed into a uniform family of branching programs with one state for each possible configuration. So we can rephrase our conjecture one more time. TEP can't be solved by a uniform family of branching programs with only 2 to the order h times a polynomial in k states. We could also state the conjecture without the uniformity condition. Now, let's look at an example of a branching program for solving TEP. To keep it small, we'll set both the height and the alphabet size to 2. When both h and k are 2, an input to TEP is structured like this. There are 6 things that we can query. The 4 cells in the root node A's table, and the 2 leaves B and C. Here's a branching program that solves it. It's organized into layers going from left to right. The starting state queries the first leaf, B. Depending on the answer, we end up in one of the 2 states in the next layer. Those states query the other leaf, C, and depending on the answer, we end up in one of 4 possible states in the third layer. Each node in the third layer queries a different cell in the root node's table, and depending on the answer, we output 1 or 2. Here's an example input. Let's see what the computation looks like. Both the leaves are 2, so we end up at the node that queries A22. Then the value is 1, so we output 1. One thing to notice here is that every layer remembers a different set of information. In the second layer, we remember node B, and in the third layer, we remember both B and C. All the lower bounds we have so far for TEP involve arguments about how many things the branching program needs to remember at the same time. One way to model this idea of remembering things is pebbling games. Pebbling games were first defined by Patterson and Hewitt in 1970. In the context of the tree evaluation problem, they work like this. Suppose we have a complete binary tree of height h, 3 in this case. We have some limited supply of pebbles, let's say that's also 3, and they all start in our hand. And we're allowed 2 kinds of move. First, we can move one of our pebbles to a leaf in the tree. And second, if both of a node's 2 children have pebbles on them, we can move one of our pebbles to that node. The goal is to place a pebble on the root node. Here's the sequence of moves that does this. We start with the leaves and work our way up. We've succeeded, because now there's a pebble on the root node. The important question is, how many pebbles do we need? In this case, we had 3 pebbles and it was enough. In general, you can solve this game with h pebbles, where h is the height of the tree, using a simple recursive algorithm. The algorithm visits each node once, so that's 2 to the h minus 1 steps. A corollary of this is that we can build a branching program that solves the tree evaluation problem using 2 to the h times k to the h states. Each step of the game translates into a layer of the branching program, and the placement of the pebbles determines which values the program is remembering. Since our strategy uses at most h pebbles at a time, the program will only need to remember at most h values at once, which requires k to the power h states in a single layer. Now, the pebbling strategy is tight. If you only have h minus 1 pebbles, no sequence of legal moves can put a pebble on the root. The proof of that is not as obvious. I'll leave it as an exercise. Now, it would be nice if we could make a corresponding corollary. Since we need at least h pebbles, maybe we can prove that the tree evaluation problem needs at least on the order of k to the h states. We'll see in a moment that this would imply that log space is not equal to polytime. For a long time, nobody could come up with an algorithm that did better, so this conjecture seemed quite plausible. The algorithm we'll present later is the first counterexample. Let's take a look at where we are. We started with this conjecture that TEP is not an L, meaning 2 to the order h times poly k states isn't enough. We saw our first algorithm. If you analyze it carefully, it turns out that the pebbling algorithm uses on the order of k plus 1 to the power h states. And the pebbling framework led to a conjectured lower bound of k to the h states. The new algorithm I'm going to show you has on the order of k over h to the power 2h plus an arbitrarily small constant times a polynomial in k states. This defeats the conjectured lower bound of k to the h whenever h is not too small compared to k. Specifically, If h is k to a power bigger than 1/2, this algorithm is an asymptotic improvement. But it's still not a log space algorithm, so the door is still open to using TEP as a way to separate L from P. Now I want to briefly mention some existing lower bounds for TEP, to give you an idea of why we found this new algorithm surprising. It turns out that under some pretty reasonable sounding assumptions, you can prove that the Pebbling algorithm is essentially the best possible. You can prove it if you assume the algorithm is read once. That means that once the algorithm reads a certain piece of the input, it is not allowed to read it again. Another assumption we can make, instead, is that the algorithm is thrifty. That means that the algorithm never reads an irrelevant piece of the input. For example, if an internal node's left child has value 3 and its right child has value 2, then it's only allowed to read the entry at position 2, 3 in that node's table, since none of the other entries matter. Our new algorithm beats this lower bound of k to the h, so as you may have already inferred, it's not read once or thrifty. Our algorithm is actually going to read every piece of the input several times. Now, I've said a lot of mysterious things about this new algorithm, so maybe it's time I told you how it works. This part of the video has two pieces. I'll begin with some techniques we use related to reversible computation, and then I'll tell you how we apply them to solve TEP. The first thing I want to tell you about is a paper that caught our attention and showed us that reversible computation is something we should be looking at. The paper is from 2014, and it's called Computing with a Full Memory, Catalytic Space. The idea is that you're given a small amount of ordinary memory to work with, and a much larger amount of extra memory. The catch with the extra memory is that it starts out filled with data, possibly incompressible, and once you're done with your computation, you need to return it back the way it was. Surprisingly, the authors found that the extra memory seems to help. With only a logarithmic amount of ordinary memory, but a polynomial amount of borrowed memory, you can compute many things not known to be computable in log space, such as the determinant of a matrix, or anything in non-deterministic log space. We stumbled on this result when we were trying to prove a lower bound for the tree evaluation problem. We had the following idea for a proof. First, at some point, you need to compute the left child of the root, node B in this diagram. Then, you need to keep that in memory while you compute the right child, C. That uses up log k bits of memory, in addition to the subroutine that's computing C. Therefore, the argument goes, every level you add to the tree adds log k bits that your algorithm needs to remember. The catalytic space result effectively shows that this approach will never work. Even if we could argue that you need to remember B while you're computing C, this result says that the subroutine computing C can borrow the memory being used to store B. The history of the techniques we use goes back pretty far. A 1989 paper by Barrington showed that if you restrict branching programs to have just 5 nodes in every layer, you can still do a lot with them. A later 1992 paper by Benor and Cleave showed how you can do a lot with register programs that use only 3 registers. Both of these papers show how you can trade time and space in order to make algorithms that use an extremely limited amount of memory. Another thing that they have in common is that they use reversible operations. The basic ingredient in our algorithm is reversible operations on registers. The model is that we have n inputs, x1 through xn, and m work registers, r1 through rm, and their values are all in some ring R. We're interested in reversible instructions. For example, the first instruction here adds register 4 times input 1 to register 5. We can reverse that instruction by subtracting instead of adding. When you run these two instructions in sequence, it's the same as doing nothing. For any register rj, let's define tau j to be its initial value before our computation begins. Now, suppose we have some function f we're interested in computing. I'm going to define something called cleanly computing f. A sequence of reversible instructions cleanly computes a function f into register I if, once the computation finishes, the new value of register I is its old value tau I plus f, and every other register is unchanged. Rj equals tau j for j not equal to I. Note that we're allowed to use these other registers, as long as we make sure to undo all our changes. Since each instruction is reversible, we can reverse the entire sequence by running the inverses of the original instructions in reverse order. If we do that, the result is a clean computation of -f. There are two reasons we like this definition. The first is that it's designed to help us reuse memory, as we'll see later. The second reason is that we can translate register programs into branching programs. If we can cleanly compute f with m registers and L instructions, then we can turn that into a branching program with L+1 layers, each containing r to the m states, in order to remember all the register values. So we can design our algorithm using register instructions and then convert it to a branching program. Now let's try some examples of clean computation. For our first example, suppose we want to cleanly compute x1 plus x2 into register 1. We can do this with two instructions. First add x1, then add x2. After we add x1, the value of the register is tau1 plus x1. And after we add x2, the value of the register is tau1 plus x1 plus x2. By definition, we've cleanly computed x1 plus x2 into R1. For our next example, let's say we've got a subroutine P1 that cleanly computes a function f1, and a subroutine P2 that cleanly computes a function f2, and our goal is to compute the product f1 times f2. The program looks like this. We can think of it as being made out of two interlocking pieces. The first piece is calling the subroutines P1 and P2. We first call P1, then P2, and since everything's made out of reversible instructions, we're then able to run P1 backward and then P2 backward. The other piece is adding and subtracting R1 times R2. Since the subroutines are modifying the contents of R1 and R2, this has a different effect each time. So let's see what happens when we run the program. We start by running P1. After it's finished, register 1 has value tau1 plus f1, and the other two registers have their original values, tau2 and tau3. The next instruction subtracts two terms from register 3, leaving a value of tau3 minus tau1 times tau2 minus f1 times tau2. As the program continues, different terms are added and subtracted from register 3. At the end, register 3 holds its original value plus f1 times f2, and the other registers have been restored. That means we've succeeded. Now, we've computed f1 times f2, but what did it cost us? Well, we had to make 4 subroutine calls, P1 and P2 forward and backward. But this algorithm is extremely efficient with memory. Notice that P1 and P2 are allowed to use all of our memory, as long as they can restore it when they're done. There's no memory that needs to be set aside for the parent routine's exclusive use. I like to think of these programs as borrowing the memory they use. Now let's talk about how to apply these techniques to solving the tree evaluation problem. This is the last part of the video. We want to build a reversible computation to compute the value at the root node of the tree. In order to do that, it will be helpful to have an algebraic formula for that root value. From here on, our ring will be the integers mod2, meaning registers will store bits. I'll introduce some notation. Brackets x equals y is an indicator, which equals 1 if they're equal and otherwise 0. Now, suppose we have some node v with two children L and R, and this is the table at that node. Let's try and build a formula for the indicator v equals 1. Well, there are 3 ways that node v can be equal to 1, corresponding to the 3 times 1 appears in the table at node v. We can turn this into a formula with 3 terms. The terms say either L equals 2 and R equals 1, or L equals 2 and R equals 2, or L equals 1 and R equals 3. Now let's write the general formula. Let's say that f sub v is the table of values at node v. In general, we take the sum over all possible values y and z for the two children. Inside the sum, we check node v's table to see whether each term should be included. We multiply that indicator by the indicators L equals y and R equals z. With that formula in hand, let's try to build a recursive algorithm. I've left our formula at the top of the slide for reference. Our algorithm's goal is to compute the formula, which determines whether node v has value x. The algorithm is parameterized by the node v, the value x, and some target register I. If node v has value x, it will flip the bit in register I. In other words, it assigns Ri plus the indicator v equals x to Ri. If v is a leaf node, then the value of v is directly available as part of the input, so we can do this in just one instruction. If v is an internal node, then we compute this formula by looping over all k² possible values for y and z, and adding each term to Ri one at a time. Each term includes a product of the indicators L equals y times R equals z, which we compute using the multiplication algorithm. This requires 4 recursive calls to check node, and 2 auxiliary registers, j and j prime. We use a total of 3 registers. Register I holds our output, and 2 more registers, j and j prime, are required by the multiplication algorithm. Since we're using clean computations, the calls to the subroutine are free to use those same 3 registers, so we really don't need any more than 3 registers, including all the recursive calls. If we convert this to a branching program, those 3 1-bit registers translate to 8 states in each layer. The length of the program is 4k² to the power h minus 1, since at every level we make 4k² recursive calls. This isn't very good. Our original pebbling algorithm just uses k plus 1 to the h states, so we'll need another trick if we're going to beat it. Let's take a closer look at what's going on in this for loop. Each iteration of the for loop is using the multiplication lemma to combine the indicators L equals y and R equals z. If you remember the multiplication lemma, it looks kind of like this. We make 4 calls to our subroutines for checking L and R, and in between those 4 calls, we update our final output register Ri. I've colored the recursive calls in blue. The for loop just means we do this whole thing over and over again, k² times. It turns out that we can completely parallelize this. All of the instructions on the first row can be run at the same time, with one recursive call that checks all of the possible values for the left child. We can do similar things for the other lines. This means that instead of 4k² recursive calls, we only need to make 4. The catch is that instead of 3 registers, we need 3 times k, since each recursive call needs to return k different indicator values. We can think of the output of the subroutine as a k-bit string, where exactly one of the bits is 1 and the others are 0. We call this a one-hot encoding. So how efficient is this strategy? Remember that the pebbling algorithm uses on the order of k plus 1 to the h states. This new parallel algorithm uses 3k registers, so each layer of the branching program will have 2 to the 3k states. It calls itself recursively 4 times, which means that the number of layers is on the order of 4 to the h times k² extra work that needs to be done. In total, we have on the order of 2 to the 3k times 4 to the h times k² states. When k is large compared to h, this is much worse than the pebbling algorithm. But when h is asymptotically larger than around k over log k, this algorithm is an improvement. The 3 times k registers are really hurting us, so the next thing we tried was a binary encoding. Instead of k bits, use log k bits to represent the value at the node in binary. The benefit here is that we only need 3 times log k registers instead of 3 times k. The trouble is, we end up needing to multiply more than 2 values at once. Our formula has degree 2 log k. We found that we needed to make k² recursive calls in order to multiply 2 log k values, resulting in a total of k to the 2h plus order 1 states. This is strictly worse than the pebbling algorithm, but it's still a useful stepping stone. By interpolating between the 2 encodings, you get an algorithm that does asymptotically better than pebbling, as long as the height of the tree is at least k to the power 1/2 plus any small constant. In conclusion, we presented a new algorithm for the tree evaluation problem, which is the first improvement since TEP was introduced 10 years ago. It is not a log space algorithm, so TEP remains a possible approach for separating P from L. There are two basic directions for future work. The first is to improve the algorithm. The main limiting factor seems to be computing products. The binary encoding algorithm didn't work because the number of recursive calls we have to make at each level is exponential in the degree of the polynomial we're computing. It would be nice to be able to improve that. We're not the first to point out this direction. The other direction is to go back to proving lower bounds for the tree evaluation problem. If you remember, I briefly mentioned that we have lower bounds for two restricted classes of algorithm. The first is read-once algorithms, which are never allowed to read the same part of the input twice. The second is thrifty algorithms, which never read an irrelevant piece of the input. Our new algorithms violate both of those restrictions. We read every single part of the input, whether it's relevant or not, and we do it over and over again, using repeated computation to save memory. Thanks for watching, and I hope to see you at the first fully online stock.